Hello, class. Okay, so we're going to do one more example of Ampere's law, where we have a device called a toroid. And basically, what it is, you take a solenoid and turn it into a donut. So instead of just a straight cylinder, you have this donut shape, and you just wrap a wire around it. Yeah, that's the picture. And we have a magnetic field inside the toroid, just in the region, like in between. Yeah, so yeah, again, we just fold this around into this donut shape. So like in the inner part, we have a magnetic field, but we can see that the magnetic field outside the toroid is going to be zero. Like, let's draw an Amperian curve here. Then the integral of B dot ds, that's going to be equal to 0 because there's no current passing through this one. Similarly, if we draw one outside, now we do have wires crossing the surface. However, they are we have an equal number going into the surface as a number coming out. So the total current is 0. So what we have both inside the toroid and outside of it, we have this result. So for outside, or in or out. We have the integral of B dot ds equals 0. Now, a very important point though, just because the integral is 0, that does not mean that the magnetic field has to be 0, even though in this case it is. Like, you could have it so that, you know, in some cases it's positive, in other cases it would, like, when you break it up into pieces, some pieces may be positive and others negative, so they add up to 0. But that is not the case here, just due to symmetry. Like, in order for B dot ds to exist, but not be, but still add up to 0, you know, it'd have to be like in this circular pattern. We'd have to have at least components here, like going into the board or out of the board. That wouldn't do anything. We're doing B dot ds along the boundary here, along this curve. And so we'd have to have a component of the magnetic field in the direction of the curve. So the only way we could have a magnetic field that's not 0, where we do this integral and get 0 as our result, is if it was somehow like just like horizontal or something. So when you're going one way, you get, say, positive, and then the other way, negative. That's the only kind of realistic scenario where we could get them to cancel out, but that wouldn't be allowed based on symmetry. So the magnetic field, not really a rigorous proof of that, but yeah, the magnetic field in here or outside the toroid is 0. Now to find inside like in the region in between the wires, let's say that this is our loop here. That is a distance r from the center of our donut. And from symmetry, the magnetic field lines have to be circular. And the direction here is determined by the right-hand rule. So let's do that. Let's look at this wire here. The magnetic field lines circle around, where like up here they're pointing to the left, they loop around inside, they're pointing to the right. Similarly for these, into the board, up here they would circle around to the right. So yeah, the magnetic field lines curl, in this case, clockwise around the interior of the toroid. And they have to be circular just from symmetry. And so if we draw a circular line, we immediately get the result that the integral B dot ds is BDS. Let me draw the circle on it as well. Okay, so the dot product are always parallel to each other along our curve, so that makes our life easier. And also, we can take B out because it's constant. So the integral is just B times 2 pi r, and that's equal to mu naught times I, where I is the current that's crossing this inner region here, what's inside our circular region. And again, we're tracing it clockwise, so inwards is positive. And these wires here are outside, so it's crossing just all the wires that are crossing it are going into the board. It's just the ones on that interior side. And so let's say the total number of loops we have is n. And so we have B B is mu naught Ni over 2 pi r. So this is actually different than a solenoid. Inside a solenoid, the magnetic field is constant, but here it depends on the radius. You look at the inner radius here, the magnetic field line is stronger because r is smaller here. The farther away you go, bigger r is, the weaker the field gets. So that's a toroid. And that has some applications. One application of this is in hydrogen fusion. They've been trying for quite a while to make hydrogen fusion a reality. So there's two types of nuclear reactions, basically. There's fission, when you have very heavy atoms like uranium or plutonium. When you break them apart, they release energy. So that's called fission. That's what you get from like bombs, or like just the regular, like the atomic bombs they made in the old days. The other type is fusion. And that's when you take light elements and make them combine, and they release energy by combining with each other. And that's what's going on in the sun. Our sun takes elements like, there's different reactions going on inside the sun, but one of the reactions, you can have two hydrogen atoms collide and form something called a deuteron. It's basically one proton and one neutron, and they release energy in the process. So that's one thing that's going on in the sun. But another thing that's happening, there's something called the carbon-nitrogen-oxygen cycle, where it's this kind of long process, but ultimately the result is it converts hydrogen into helium. Like you start with a carbon atom, and it gets hit by a hydrogen atom. And then it gets hit again, and it gets hit, and it can turn into nitrogen, gets hit again. Ultimately, it gets hit 4 times, and it goes from carbon to nitrogen to oxygen, and then it can break apart again into a carbon atom and a helium atom. So the result is you're putting 4 hydrogen atoms into it, and you're getting 1 helium atom out. And that releases energy in the process. And the carbon and nitrogen and oxygen are basically recycled. You start with carbon, then it turns into nitrogen, then it turns into oxygen, and then it breaks apart back into carbon and a helium atom. And so that carbon can then go through the cycle again and again and again. And so that's the carbon cycle, or carbon, nitrogen, oxygen cycle. And I think for a star like our sun, roughly half of it, half the energy it produces is that carbon cycle, which converts hydrogen into helium. But, the rest of it is just hydrogen atoms colliding with each other and forming heavy hydrogen. Basically, it's a proton and a neutron, and that releases energy as well. So when you combine things, that's called fission. And fission would be great if we could, as a source of energy, because normal nuclear energy we use is kind of dangerous. They have meltdowns occasionally. It's happened a few times. But also, using things like uranium and plutonium, that decays into radioactive elements. And it's pretty much safe to say that all these high-level radioactive elements that we've created since we developed nuclear technology in the 1940s, it's all still there. And basically all we do is try to bury it as well as we can, and it keeps leaking. I guess in Washington State, there's this disaster that's been going on for the last decade or so, where they buried a ton of this very radioactive stuff that remains radioactive for thousands of years. And it's like leaking into a river. So radioactive waste is a huge problem when you're dealing with things like hydrogen and helium, like uranium or plutonium or thorium. It produces very dangerous stuff that we have no way to really get rid of. So we just have to deal with it. And it has such a long half-life, it essentially sticks around forever. If we could develop fusion, that would be a whole different story. Because we'd plug in hydrogen, and it would create very low-level radioactive waste that's much less harmful. And it would be a great source of energy. The problem is that it's extremely difficult to make sustained helium reactions. The sun can do it because it's enormous and it has gravity that's, it's basically a big ball of gas that's being compressed by gravity, which heats it up enough to start these nuclear reactions, and the gravitational field can contain it. But to do it on Earth, they try to use magnetic fields to contain the hydrogen and helium, this plasma, and that's an extremely difficult thing to do. They invest very little money in this, so progress has been slow. But in Europe, there's this project going on that it's more of a testing type of thing now, but if that works, they think they'll be able to scale it up and actually produce commercial power using fusion. And that would be great. It's a very clean source of energy that does not leave any significant radioactive waste behind. But yeah, that's something we kind of just have to hope for, that actually works out. And that would be a great source of energy, but as of now, it is not at all practical. They can't, they have made short duration sustained fusion, but it's not practical because it takes an enormous amount of energy to get the reaction going, and we don't get enough energy out of it. We actually put more energy into it. And so that's what this one they're pretty close to developing, that could actually get more energy out than we put into it. And if that test works out, then down the road they'll be able to make actual commercial reactors, if they can prove that design works. Now, I think very recently, I forgot what university, but they may have come up with a kind of another way that I think would be an improvement, and hopefully that would work as well. But so again, that's just one application of a toroid. But mainly we're going over this just because that's another thing where we can calculate a magnetic field due to Ampere's law. So just like Gauss's law, there's very few examples where that's even possible. So why don't we do the ones that we can? Because it requires that same type of symmetry we dealt with in Gauss's law. But I think we'll kind of stop this here. And yeah, that'll be it for now.